So Monday's lecture was a very important one, so I want to just start by reiterating the main points and make sure I never lost you never lost the forest for the trees. So we worked pretty hard to prove a formula, but the good news is the formula is going to be very useful. The hard work will pay off. I'm going to use this over and over again already today. Okay? So what we did is we showed that for every auction, optimal or not, didn't matter. If you look at the payment, the expected revenue, so we're averaging, again, over the distributions that were given, which define the input distribution. So just evidently, this would be the expected revenue of an auction. But we showed that actually this can also be written with an expression that doesn't reference the payment rule at all, which again is kind of shocking given that the whole thing we're trying to maximize is the payments, but rather references only the allocation rule of a mechanism, the virtual surplus. Okay? So this was the main thing we proved Monday. And let me just remind you where phi I refers to the virtual valuation of a bidder. It depends on its value. It depends on the distribution from which the value is drawn. And the formula is VI minus 1 minus the distribution function of VI over the density at VI. Okay? Now, I already gave you an application of this, a very important application on Monday, which is under an extra assumption on distributions, this actually tells us exactly what the optimal auction is. In fact, in every single parameter environment, this tells us what we should do, at least in principle. Right, so the problem definition is to make this as large as possible. We've reduced that to making this as large as possible. And the obvious way to do that is just to, so this, remember this looks a lot like surplus. The only difference is instead of values, we have these coefficients that are virtual values. And so what did we do in surplus? We just said, well, give us the bids, let's treat them as the valuation, and let's just pick the outcome with the biggest surplus. So we're going to try exactly the same thing here. We get the bids or the values, we compute the virtual values, we're just going to pick the allocation that has the largest virtual surplus on this particular input. So I'm going to call that the virtual surplus maximizing allocation rule. So formally, X just picks the argmax. Okay, so it looks over all of the feasible solutions. Remember, a single parameter environment. This is just which things are feasible, like in a single item auction, and most one person gets the good. And you just look over all feasible solutions, which one has the biggest virtual surplus. Okay? So this is exactly what we studied in surplus maximization, except the VI has been replaced by a phi of VI, by a virtual valuation. So if this allocation rule happens to be monotone, then we're done. So then it is optimal. And again, by optimal this week, I always mean maximizes expected revenue over all DSIC auctions. That's what optimal means. Okay? So this characterizes the revenue of every auction if just making it as big as possible separately on each input actually gives us an implementable allocation rule. We're done. So that's the first thing we realized. The following fact we only thought through in the special case of a single item auction, but actually it's more general, as I'll ask you to prove on the exercise set. So if every distribution is regular, and we defined this Monday. I'm actually, for simplicity, going to make the condition a little stronger starting today. It's going to be that the virtual valuation function is strictly increasing. Monday we said non-decreasing. Let's say strictly increasing, just to make our lives a little simpler. Okay. So as long as, and so remember the uniform distribution gave us a strictly increasing function. Many other distributions do as well, as you'll see on the exercise set. Not all distributions give us regular, but many are. In that case, then this totally works out, this design paradigm. Okay? So then it is monotone. And here by it, I mean that virtual surplus maximizing allocation rule. So when we have regular distributions, and again, this is what we proved by the end of last lecture, any single parameter environment, any set of regular distributions, we actually know what the optimal auction is. We totally solved it. It's this. Okay? This is how you choose the allocation. You always choose it to maximize virtual surplus. It's monotone. Meyerson's lemma gives us the suitable payments. Okay? So we've solved the problem just into the regularity condition, full generality. Now, we also spent a little bit of time interpreting this on Monday. So single item auctions, where again, it's very easy to understand the feasible set, and most one bidder gets the good. You just have to choose whom. So if you have a single item auction, and also you have IID, regular bidders, we observe that in fact, this rule is a very simple one. Okay? To maximize virtual surplus, you give it to the bidder with the highest virtual value if there's someone with a positive virtual value. And by virtue of there being IID, everyone has the same virtual valuation function. Virtue of being regular, it's an increasing function. So the highest virtual value bidder is also the highest value bidder, i.e. the one chosen by the Vickrey auction. So if you actually think through what does this rule look like in this special case, it's an auction that we know and love, namely the Vickrey auction with a suitable reserve price. So in other words, under these assumptions, you can actually implement the revenue maximizing auction. Despite the richness of the things you could try, eBay is already going to do it for you as long as you choose the opening bid appropriately. Okay? So this is fantastic. This is just a totally killer application of auction theory. So we sort of did this very rigorously and formally, but what popped out at the end, we got a very crisp, very conceptually meaningful, and downright practical auction. Okay? That's what's being advocated by the theory to use to maximize the seller's revenue in this situation. So that's great. That's really exactly, that's the best case scenario. Okay? When something you can really use just pops out of the theory without any further work. That's what we got. So the plot thickens, however, when we make the environment a little bit more complicated. And so this is the segue into today's topic. So if bidders, so I'll keep all the assumptions exactly the same, except I will not assume that the bidders are IID. Different bidders I will have different F sub i's. But all the F sub i's are regular, and it's still a single item auction. So if bidders, not IID, turns out things get weird. Okay. So what do I mean? Well, for example, right, so, this thing over here, Vickrey auction with a suitable reserve price, you can explain this to someone who's never had any auction theory. Okay? You just say it's eBay, right, with some opening bid. I don't know how to explain the payments in this auction without referencing virtual valuations, which of course would have no meaning to someone who didn't study auction theory. Okay? So the payments, even though they're just these critical bid payments, they're still pretty hard to interpret if you haven't sat in on this week's lectures. You also get weird and sort of provocative things, like the winner in this optimal auction need not be the highest bidder. And that's also something I'll ask you to work through on the exercise. Okay? It happens even in very simple examples. So the optimal auction advocated here really has these properties that we never see in the world. Okay? And in some ways, there's no way out. Right? So if you 100% believe in the model you set up, you 100% believe in your distributions, your FIs, and you want 100% of the optimal revenue, this is the only way to do it. Okay? There's only one allocation rule that's going to accomplish it, and for the allocation rule, there's only one payment rule that's going to make it incentive compatible. So you're stuck with this. Okay? So, but this is unsatisfying, right? So this theory is a little bit harder to interpret or apply, that it gives us these sort of strange auctions that we don't see in the world. And so the theme for today's lecture is, well, can we get much more plausibly implementable auctions? And of course, we can't if we want 100% of the optimal revenue, but giving up a small amount of revenue. Okay, so get almost optimal with a much simpler and much more practical auction. Okay? So that's the motivating question for today. Are there simpler, more practical, more robust auctions that we can prove are near optimal? Okay. So for context, let me point out that this is the second time we've turned to approximation to get us out of a bind. Does anyone remember the first one? It's last week. Say it again? Knapsack, yeah. So what did we not like about sort of the optimal auction in that case? Right. It was computational intractability. Right. We needed to solve an NP-complete problem to implement the auction. So to recover polynomial time, we relaxed exact optimality. And something similar, though a little more vague, is going on here. We solve for the optimal auction, and it's out there, and we know what it is. And again, we sort of don't feel comfortable saying this is something we're going to implement. It's not because we think it's going to take an exponential amount of time. It's just because there's sort of no precursors out there in the world of how to sort of explain this auction to people and get them to use it. Okay? So, I'm going to leave words like simple, practical, and robust kind of safely undefined in this lecture. Frankly, there's a lot of work last 5 years on exactly this theme. And it's basically an open question, an important open question, to figure out the right way to define a simplicity of auctions so that we kind of have this entire theory on solid ground. But what we do have over the past 5 years are a number of concrete examples, situations where there's an auction which is evidently simpler than the optimal one and which is not too far away in terms of revenue. And so those are some of the things I'll give you a taste for today. Question?
Are we swapping surplus with revenue? So we don't care so much about surplus anymore?
Yeah, this whole week's about revenue maximization. Mm-hmm. This whole week is about revenue maximization.
And we're kind of ignoring surplus maximization? Or at least it's...
Well, I mean, if you're going to talk about optimizing something, you kind of got to pick an objective. There's interesting work on trade-offs between the two, but I'm just going to treat each in turn. Other questions? Okay. All right, so another point I want to make is that, so the basic theory we covered on Monday, it's very essential, crucial stuff. It was developed mostly by Roger Myerson, who's an economist. He wrote the corresponding paper in 1981. He won a Nobel Prize a few years ago for that paper as well as other contributions. What we're going to be talking about today, these approximation guarantees for simpler, more practical auctions, this is much more recent. Okay, so this has been done almost entirely in the past 5 years or so. It's been done mostly in the computer science literature and community. Okay, so in the econ community, they've studied approximation very little. Okay, they have not really thought about what it can buy you. So this is much more recent stuff I'll talk about today. All right. So next is what may seem like a digression. I hope a fun digression. But it will be relevant. It will give us our first example of a simple near-optimal auction. I want to tell you about something called a Prophet Inequality. And given the context, maybe you think I'm using the wrong spelling for profit. Maybe you're expecting P-R-O-F-I-T. But it turns out this inequality, was not developed for auction theory per se. Okay, so that's the profit, and I'll explain why. And this is a cool result. And this is one of those results where pretty much anyone who likes math is going to like this result. Okay, so it's just something you can sort of whip out at your next nerdy cocktail party to make some small talk. Don't pretend like you don't go to any of those. So here's the setup. So there's one person playing a game, and the game iterates through n stages. Okay? In stage I, you will be offered a prize with some value. Okay, so I'm going to use pi I for the value of the prize. And as the person playing this game, you know GI in advance. Okay, so you know G1 through GN. But you only learn pi I when and if you get to the ith stage. Okay? I should also mention that the distributions are independent. And the way the game works is at each stage you have a decision to make. Okay, so there's some prize, you know, worth $170 or whatever. Maybe you're at stage 7 out of 15. And either you pick the prize, okay, you walk home with your $170, game ends. Okay? Or you discard it and continue. Okay? It's up to you. You know what G8 through G15 are. You don't, of course, know what the pi 8 through pi 15 are. If you did, it would be trivial. Okay? Yep.
What are pi and g?
Pi is a number, G is a distribution. Is the game clear? And is it clear that it's not obvious how to play it? So there's an obvious trade-off. Do you stop relatively early, possibly missing out on some large prize later on? Or are you very patient with the possibility that you'll be stuck accepting some very lousy prize in the nth stage? Okay. Yes?
So you're offered a prize in each stage?
Yep.
Okay.
In stage I, offered prize pi I. So here's the very cool fact. Okay. So there exists a strategy, in fact, a strategy with a very special form. The guarantee is going to be competitive with what a prophet could obtain. What do I mean by prophet? I mean someone who has full clairvoyance and knows in advance what pi 1 through pi n is. A prophet's just going to wait till the biggest prize shows up and take it in that stage. So the payoff enjoyed by a prophet will be the expected value over the realizations of the pies of the largest prize. Okay? This is what a prophet can obtain in this game. Now, obviously, we're not going to get this much. Okay, that's ridiculous. As soon as you had 2 prizes, right, you get the first one, it's like $100. As long as there's some chance that the second one might be above 100 and might be below 100, after the fact, you might regret whatever your decision is in stage 1. Okay? So there's no way you'll do as well as the prophet. A priori, I think most people's intuition, including yours truly, is that there's no reason you should get close to this at all, ever. It's not that there's any strategy smart enough that can compete with someone with so much more information than you have. Okay? Nonetheless, there's a strategy which gets half of what the prophet gets, guaranteed, no matter what the GIs are. Okay? So in fact, it's not even a complicated strategy. It's what's called a threshold strategy. A threshold strategy with threshold t works as follows. At the very beginning of the game, I look at G1 through Gn, and I pick some threshold t. Okay? And then in some stage, if I get a prize with value at least t, I take it. Okay? And if not, I don't. And I never change. Doesn't matter what, what pi's I see. I don't even, in the final stage, when there's no future, stoop to accepting a prize less than t. So obviously, these threshold strategies are not optimal. Okay? That's not what I'm claiming. I'm not claiming they're optimal. I'm just claiming that they do almost as well as a profit. Okay? So even a threshold strategy works. Okay, so that's an addendum to the theorem. Where again, what this means is you accept pi I if and only if pi I is at least t. Okay? All right. So now let me show you the proof. Some notation I'll use whenever I have a number, a real number, I'll write that plus if I just want to take the max of that number and 0. Okay? So what I'm going to do is I'm going to do a generic analysis for how well a threshold strategy does. It'll be parameterized by the threshold t. We will choose the right threshold t at the very end of the proof, once we understand the trade-offs between bigger and larger t's. Okay? I mean, qualitatively, I hope the trade-off is clear. The bigger the threshold, the more money you'll make if you're so lucky as to see a prize that's at least t, but the greater the chance you won't get any prize at all. Okay? The lower the threshold, the more likely you'll get a prize, but who knows if it'll be any good. Okay? So one other quick piece of notation. Q of t, so again for given threshold t, Q of t is the probability that you wind up empty-handed. Okay? That every single prize is less than your threshold. And that, of course, is going down as your threshold, as your bar is going up. Questions? So the plan, so what the theorem is about comparing two things, right? It's about comparing the expected prize, if any, that you get from this t threshold strategy to the expected profit or the expected value that the profit obtains. Turns out those two expected values seem hard to compare directly. So we're going to do something which is very common in approximation guarantee proofs like this one, which is we're going to replace one or more quantities that are hard to work with directly by suitable upper or lower bounds that are easier to work with or easier to understand. So what I'm going to show you first is a lower bound on the expected value obtained by this threshold strategy. Okay? So it'll be something that's even worse than our threshold strategy. And I'll show you an upper bound on how well the profit does. So it'll be even better than the profit. Okay? And I'm actually going to show that those two things which are even farther apart, even those are within a factor 2 of each other. Okay? And these lower and upper bounds will be easier to compare directly than the two quantities we started with. All right. So I got to give you a lower bound and upper bound. They both have a couple inequalities, but they're not too hard. So let's start by lower bounding how well a threshold strategy does. Okay? Okay, and again, we want lower bounds for this one. Well, there's some probability our payoff is 0. So just to remind everybody, what's that probability? Q of t, that's how I defined it. At Q of t, you get nothing. So 1 minus Q of t, you get something. Okay, and when you get something, its value is at least t. So a totally valid, and actually a very good first cut lower bound is this. The probability you get a prize times the minimum value that prize could be. So it turns out to make this proof work, we need a somewhat sharper lower bound. Again, this is correct, but we want to make this right-hand side a little bigger. Okay? So, so why is this not an optimal lower bound? Well, what if our t is 100, and then one prize shows up that's above t, and it actually is 120? Okay? Then the value we get is 120. It's not just 100. Right? We don't just get the threshold. We get whatever the actual value is, which might be well more than the threshold. Okay? So that sounds like a good idea. We want to actually put here kind of like the pi I for the prize above t that we get. But here's what's kind of annoying, right? So suppose there are actually two prizes above t. Like our threshold's 100. There's one prize that's 120, and there's another prize that's 130. What can we say about the value that we get?
First one.
Right. Okay, so whichever of those happen to come first in the ordering, it might be 120, it might be 130, that's the one we're going to pick. So it's not like, just because there was a 130, it's not like we can really say we got 130. It might have been blocked by something that was 120 that was earlier. So it turns out we can get away with just totally punting on this complication. All right? So here's what we're going to do, and it'll make it clear it's a lower bound. If there more than one prize bigger than t shows up, I'll just say, I'm only going to credit myself t. Okay? Clearly I get more. I get one of these VIs that's bigger than t, but I'm only going to give myself t, which surely I get, because whatever prize I pick, it's at least t. On the other hand, if exactly one prize gets instantiated to a number bigger than t, then I'll give myself the extra credit of VI minus t. Okay? And that'll be the lower bound. So let's just write that out. So remember this says at least one prize is at least t. So I always get t in that case. Plus, so I'm going to sum over the items or over the stages, and at a given iteration I, I'm going to say, well, sometimes item I, prize I will be bigger than t and everything else will be less than t. And in that case, I'll give myself the extra credit of VI minus t. Okay, so sum over the candidates for being the sole prize above t. And so what is that going to be? Yeah, okay, good. So here's the extra credit, pi I minus t. And the case I'm interested in is where prize I exceeds the threshold and everything else does not. Okay? So this is the bonus I'm going to get. Now, the formula is not quite right because I have to multiply this times the probability of this actually happening. Right? Maybe this never happens. Right? But so this gets multiplied times the probability of this stuff, of what I conditioned on. So I'm going to write this. I'm going to actually factor this. Remember, the distributions are independent. So this event and this event are independent. So let me just write probability that pi I is at least t times the probability that pi j is at most t for all j not equal to I. Okay? And again, what this means is we just give ourselves the extra credit when there's exactly one prize that's at least t. All right, so let me simplify this a little bit. So I already mentioned, we already used the fact that the GIs are independent when I wrote these probabilities this way. Let me use it again. Because the GIs are independent, the fact that these other prizes are less than t has no bearing on the expected value of pi I minus t. Okay? So by independence, that conditioning is irrelevant. Okay. And so now let me just clean this up. Instead of actually just looking at this expectation condition on the event that it's non-negative, I'm just going to write this with my plus notation instead. Okay? Just for simplicity. So what do we have? 1 minus q of t times t plus sum over the stages times the expected extra credit we get in stage I times what's left, the probability that everything else is less than the threshold. Okay? So all I did was combine this and this into the expected value of the non-negative version of vi minus t. Now, what would be really cool is, right, we have this 1 minus q of t here, so that's some probability. We have some probability here. Do you see any relation between this probability and q of t? Just to make this a little simpler. Say it again. Something, I'm looking for something simpler. I don't think so. So what is q of t? Q of t is the probability that nothing is above the threshold. What's this? This is the probability that everything other than I is below the threshold. Right? So this is a less stringent condition. Right? So this is a higher probability. So we can lower bound this by q of t. Okay? The smaller event that everything is below the threshold, including I. Okay? So that ends step 1. We can lower bound how well we do by 1 minus the probability that we get nothing times t, our threshold, plus the sum of extra credit terms. Okay. Say it again. Oh, it should be pi, sorry. I've been too immersed in auction theory these last couple weeks. Questions? So that's our lower bound on our value. So now we want an upper bound on the value of the profit, which hopefully we can compare very easily to this lower bound. That was the whole point of this exercise. Yeah.
How do you go from step 1 to step 2? How do you remove the probability that pi again equal to t from that?
How did I get from what to what?
I mean, you said pi independence, you remove that, right? How do you do that?
So the prizes are independent.
Yeah.
Right? So what is that expectation about? That expectation is about the ith prize. So telling you anything about the other prizes has no bearing on the value of that ith prize. So I can just cross out the conditioning. Other questions? All right, so upper bound on the profit. This is easier. And so we just kind of want to like copy this format somehow, right? To make them easy to compare. So we've got this t here. So what are we trying to upper bound? Remember, we're trying to upper bound the profit, which is just the value of the biggest prize. And because I somehow want t to get involved, right? There's no t here. Notice, right? This is the profit. I could care less about a threshold. So in the analysis, I have to get the threshold involved so I can make a comparison. So let's just sort of add and subtract it to get the ball rolling. So remember, we're going for upper bounds now, right? So this could be positive or negative. So it only gets bigger if I make this non-negative. And you'll see why I want to do that in a second. Shoot. Okay. So this is just a max. Now again, we're trying to have something we can easily compare up here. And so this involves non-negative versions of this involves kind of the extra credit values, the pi I minus the t's. But the biggest one, this involves the sum. But fortunately, non-negative numbers, the sum is going to be at least the biggest. So is there some value of q of t that would be kind of super convenient for relating these two quantities. By these two quantities, I mean that one and this one. 1/2. Right? If Q of t was a half, then up here, that would be a half. That would be a half. And we'd be done. Something that's even worse than our threshold strategy's value is at least 50% of something that's even better than the profit. Okay. So setting t so that Q of t, and let's notice this is actually conceptually kind of really neat, right? It kind of says like, what should you do in this kind of game? Okay, it says, well, you want to be aggressive enough so there's at least some chance you'll get nothing, right? Because otherwise you're settling for too little too often, okay? And so what's the rule of thumb? It says, well, make it 50-50, whether you get somebody or you don't get somebody, okay? And you're going to do two approximation of a profit, okay? So that's it. So that's the Prophet inequality. Okay? Any questions about that? Other than, why did I just teach you this? Yeah?
So the first inequality is inequality.
Say it again?
The first inequality is inequality.
In which? In 2. Yeah, that's a good point. That's a good point. Yeah, because this is always at least t. No, that's fine, actually. I just added and subtracted t. This is where the inequality comes in. Yeah.
So why are we choosing a half?
Because then the expression on top is exactly half the expression on bottom. We're choosing t so the Q of t is a half. Right, so we want the probability of getting a prize to be a half. 50-50 get a prize. I mean, t in itself has no meaning because we don't know the scale of the prizes. They could be in dollars or billions of dollars. We have no clue. So, yeah. Excellent question. Yeah. So does there exist such a t? So with continuous distributions, you're going to be okay. If you wanted to extend, this does extend to discrete distributions. I'm sort of debating whether to put that in exercise set 3 or not. But basically, a variation on this proof extends it, even if there is no such t. There is still always, no matter what the distributions are, a threshold strategy that gets you a factor 2. Yeah?
Are there better solutions than 1/2?
There, in fact, cannot be better solutions than 1/2. So, in fact, this bound is tight. Good questions. Other questions? All right, then let's see what we can. Let's understand the implications for the design of simple, almost optimal auctions. And in particular, what I want to focus on is exactly the simple setting where things already got weird. So I want to focus on single item auctions, where the bidders are drawn from regular distributions, but not necessarily the same regular distributions. I should say, this is just a representative result, scratching the surface of a lot that's been going on in the past 5 years. If you want to know more, I'm using this book draft of Jason Hartline's for this part of the course, and chapter 4 of his book is all about these guarantees for simple near optimal auctions. Okay, application. So single item auction, regular, not necessarily identical distributions F1 through Fn. Here's the idea, okay? I'm going to connect this to the Prophet inequality kind of sort of immediately, okay? Let's regard the virtual valuation of a bidder, or rather, the maximum of that and 0, as a prize, okay? Pi I. and from f sub I, we get some induced distribution g sub I over these pi i's, over these virtual values of the bidder. Okay? The FIs we're assuming are independent, as always this week, so the relevant GIs are independent, so the profit inequality will apply. It's not clear yet what it's going to mean, but we can invoke it and see what we get. Now here's where the connection starts to become more clear. Okay? Let's think about the optimal revenue achievable in this setting, in the single item auction. Okay? Well, as we know, it's exactly the same as the maximum possible expected virtual surplus. So let me write X star to denote the virtual surplus maximizing allocation rule. Okay. And in a single item auction, what is this? Well, this is just either the highest virtual value, or if everything's negative, it's going to be 0. That is, in a single item auction, for the optimal auction, the revenue, or rather the equivalently virtual surplus of that optimal auction, we can write as the expected value of the maximum virtual value, or 0, if they're all negative. Okay? So if we regard these things as prizes, this in fact is exactly what we were competing with in the profit inequality application. Okay? So we can regard the revenue of the optimal auction for the single item auction as the expected prize value of a profit. Okay? So let me now propose a simple auction, actually really a family of simple auctions, and I'll give you a particularly attractive instantiation in a little bit. So again, if we did the full-blown optimal virtual surplus maximizer, we could do it in principle. It's sort of a crazy mechanism, but we could do it. This is what we get. Suppose instead, guided by the profit inequality, the first thing the auction does is it looks at the distributions and it chooses a threshold T so that as we said before, so that the probability that one of these prizes is at least T is exactly a half. So that's the first thing the auction does. Then what does it do? It gets in the bids. Okay, it looks at the bidders, computes the virtual values. Anybody who's below T gets thrown out. Okay, just like in a reserve price. And if there's no one left, nobody wins. If there's one person left, obviously they get the good. There's only one person with virtual value above T. If there's more than one person with a virtual value above this choice of T, it awards the good arbitrarily. Okay? For now, let's say arbitrarily. Okay? I don't care how. Randomly, lexicographically, it's not going to matter for the analysis. There's something I forgot to tell you about the profit inequality analysis, which is relevant for this arbitrary tie-breaking. Okay, so just the claim is that any auction of this form gets within a factor 2 of the best possible expected revenue in a first price auction. Sorry, in the optimal auction. Okay? So any simple auction like this is within a factor 2 of the full-blown optimal auction. That's where we're going. To forge that link, I have to explain something that handles these tie-breaking rules. So observation about the profit inequality. All right, so I'm going to ask you to page back in what we're talking about with the profit inequality. So remember there are these prizes, and there's this threshold. When we're talking about our threshold strategy, suppose that multiple prizes turn out to be above the threshold. Okay? So as was acutely observed from the audience, what actually happens with the threshold strategies, whichever one of those winds up being first in the ordering, that's the prize you're going to go home with, because you pick the first prize above the threshold. But I claim that our factor 2 guarantee applies to an even worse version of that threshold strategy, where instead of just going home with the first prize above the threshold, you actually pathologically go home with the worst of all of the prizes that exceeds the threshold, when there are many. Okay? That's the claim. So, I erased the reason why this is true, unfortunately. The reason is because of the way we lower bounded the revenue achieved by the threshold strategy. Okay? So what we had these terms. What did the terms mean? Well, we said, well, there's some probability we get 0. Okay, that was Q of t. And then there's the rest. This is probably 1 minus Q of t. Okay? And what was the extra credit we got? We said, well, for each item, there's some chance that that's the sole unique item above the threshold. In that case, and in only that case, we get the extra credit of VI minus t. In our lower bound, whenever more than one prize was above the threshold, we just punted. We said, for the accounting, we'll just call it t among friends. Right? And even with that accounting, we proved our factor 2. So that's why even with bad tie breaking, so even if you somehow change the rules of the game for threshold strategies, that you always go home with the least valuable of everything that exceeds the threshold, you still are within a factor 2 of the profit. Okay? So that's sort of a bonus observation implied not by this theorem statement, the profit inequality, but by the way we prove that theorem. Okay? Question?
This factor of 2 thing, that's guaranteed on average, right? Rather than any reasonable circumstance.
It's about expected value. But you have to take the expected value for the profit itself. I mean, the profit's value is random as well. So yeah, it's about expected values. Good. So this is a sharper version of the profit inequality, stronger guarantee. Now let's go back to this auction. Okay? So the proposed auction is compute a threshold as suggested by the profit inequality, so that the probability that a virtual value of anybody is at least t is exactly a half. Delete all of the bidders whose virtual value is below that threshold t. If there's none left, nobody gets the good. If there's one left, they get it. If there's more than one left, an arbitrary one gets it. I don't care who. Okay? So now, applying the profit inequality to any auction of this form, right? So what can we say about the virtual surplus of any auction of this form? Okay? Well, the virtual surplus of this auction, when it awards the good to somebody, it gets a virtual, the virtual surplus is the virtual value of that one bidder, phi of VI. If there's exactly one phi of VI above the threshold. If there's multiple people above the threshold, we don't know. We get one of those phi of VIs. It's undefined which one, but all of them are at least t by definition. Okay? So the virtual surplus of this simple auction is exactly that lower bound that we had in the proof of the profit inequality, which we established is at least half of what the profit could obtain. And in this context, what the profit could obtain is exactly the maximum possible expected revenue. Okay? So that's the profit. What do we get? We get phi vi if there's exactly one potential winner, and we get t if there's more than one potential winner, and we know that that's within a factor of 2. So the expected virtual surplus of the simple, of the simple auction is at least 1/2 that of opt. And using for the umpteenth time the virtual surplus and expectation is the same as payment and expectation, this gives us a factor 2 guarantee on the revenue of any auction in this class. So just to help you interpret this a little bit better, let me actually give you a specific auction in this class, which is very easy to describe, okay? Which in particular makes relatively minimal reference to virtual values. Okay? So here's a specific implementation. So what do you do first? You set reserve prices, right? We've seen those before. Even in the IID case, the optimal auction used a reserve price. So we're used to that. Bidders have different distributions, so perhaps unsurprisingly, we're going to see different reserve prices. Okay? We'll talk about that in a second. Over in the Prophet Inequality world, we used a single threshold, okay, to decide who was in and who was out. Okay, so there was a single threshold T, but that was about virtual values. Okay, so everybody has the same kind of reserve price in the virtual value space, but those map back to potentially different reserve prices in value space. Specifically, in a specific implementation, we set for each bidder I its own personalized reserve price Ri, defined as the inverse virtual value of this threshold T. Okay? This is just saying the same thing we said before. Reject bidder I if its virtual value falls below T. Okay, it's exactly the same thing. And then if there's lots of winners, and then you just do a Vickrey auction on top. Okay? You just give it to the highest bidder of everybody who clears their reserve. So you have a filtering step, and then you run a Vickrey auction, and that's it. Okay? So this auction is now looking reasonably simple. It's getting closer to what we see in practice, closer to something you can imagine implementing. It is one specific member of this class, the whole class, that enjoys this factor 2 guarantee for optimal. Okay. So this is a canonical simple versus optimal statement. Okay. You're not optimal, but you're close, and you've made big progress on plausibility. In fact, I'd really say there's kind of only one obstacle to being a super practical auction. And is there anything bothering anyone about this auction that I proposed in the back?
We seem to have different reserve prices for different bidders.
Excellent. So the reserve price is different for different bidders. Now, you do actually see a few auctions out there where there are reserve prices specific to bidders. They're not unheard of. Even in sponsored search, generally advertisers who are deemed higher quality will have lower reserve prices. And sponsored search engines will use often more aggressive reserve prices for lower quality bidders. So you do see it a bit, but if you think about eBay, even if you know asymmetries amongst the bidders in your auction, you just get to set one opening bid. Okay, there's no way in the auction format to exploit that asymmetry in your knowledge about it. So let me give you an open question. It's actually not known in exactly this setting, single item auction, regular distributions that are not necessarily identical, how close you can get to the optimal revenue if I force you to use eBay, if I force you to use a second price auction with a single common reserve price. It's an open question. I do know some bounds on the answer. So in a paper with Jason Hartline, we proved the answer is somewhere between 2 and 4. We don't know where. Okay? So that's a paper from the EC conference 2009. All right. So that's what I have to say about guarantees for simple mechanisms in this sense. Again, chapter 4 of Hartline's book has tons of stuff on this topic. Let me levy another critique against this auction, and actually even the killer application we reviewed at the beginning of the lecture. Okay, Vickrey auction with a suitable reserve price, okay, for the IID setting. In all of these situations so far, what we've assumed is that these distributions, F1 through Fn, are known to the seller in advance. Okay? Or if you like, we're in effect assuming that it's an auction environment where you have excellent data about what's happened in the past, and you're willing to make the assumption that what happens next is going to be similar to the past. To be clear, that's a reasonable assumption in many contexts, and especially with the amounts of data that people have on lots of things now. But there's other cases, so-called thin markets, where you don't necessarily have good data or good prediction about what people's value for what you're selling is. So what I want to ask next is, suppose we didn't know these distributions at all in advance. Is there anything non-trivial we can do? So you might be worried that we're back in sort of the challenge model that we started revenue maximization with, where we knew nothing about bidders and it wasn't clear what price you could set, and that was the whole reason we adopted distributions. So actually I'm going to make a more fine-grained relaxation. We're still going to assume that there are distributions. We're still going to do average case analysis with respect to F1 through Fn. We just insist that when you design your auction, it cannot reference any distributions F1 through Fn. The auction format should be independent of distributional assumptions, but when we talk about the performance of an auction, it will be, as we've been doing all week, with respect to the distribution over valuations. So the question then will be, can we have an auction which in effect doesn't know the distributions, but whose performance is almost as good as if we did? So, such auctions, and I'll give you an example next, but the buzzword here is prior independent auctions. So prior is just what refers to as these distributions F1 through Fn. Prior independent auction just means that your auction cannot reference any distributions. It should be well defined, independent of what any distributions are, and hopefully you can analyze it and prove performance guarantees as well. So this, again, this has been, I'm only going to say, sort of one precursor result in the field, but again, this has been kind of a very hot topic the last 3 years or so. And I'm quite proud of my previous PhD students, Pierpong Dangwannatai and Chi-Chi Yan, who have been sort of the main pioneers in this area. All right. But I don't want to tell you about a result from the last 3 years, although if you're interested, chapter 5 of Hartline's book has plenty of stuff on it. Rather, I'm going to tell you about an older theorem from '96. It was proved by a couple of economists, actually, including Jeremy Bulow, who's here in the business school. But I think it feels like a very computer sciencey theorem to me. And it's one of those ones where you look at it and you're like, man, wish I could have proved that. It's a cool result. So, a theorem by Bulow and Klemperer. So I'm again going to state it for a single item auction, although you can generalize it. And now we're going to go back to assuming that the bidders are IID. Okay? And as usual, we'll assume that their valuations are drawn from a regular distribution. And so what the Bulow-Klemperer theorem compares is the expected revenue of the Vickrey auction, so just the usual second price auction we talked about on lecture 2. And it compares that to the expected revenue of opt. Okay? And this is a simple enough setting we know what opt is, right? So what is opt under these assumptions? So this is the simple case, right? The IID case. So that's just the second price auction with a single reserve. Okay? So this is the Vickrey auction, in effect, with a reserve of 0. This is just a Vickrey auction with the suitable reserve, which is the inverse virtual value of 0. Okay? So that's what the theorem is about. It's about comparing those two quantities. Right? So which one of those quantities is obviously bigger than the other? I mean, the right side's bigger, right? On the left side, we have an auction. On the right side, we have the best auction. But let me tell you which way the inequality goes in the Bulow-Klemperer theorem. It goes that way. So what's the catch? Here's the catch. On the right side, we have n bidders. N is any integer at least 1. On the left side, we have n plus 1 bidders. On both sides, we have the same distribution, capital F. On both sides, we're taking IID draws. On the left side, we're using a suboptimal auction with 1 extra draw, and we do at least as well. Super cool. So the usual interpretation of this result is, you can obsess over your auction format and over the distributions if you want, but maybe what's really important for making money is making sure it's competitive. They bring extra people to your auction. That's probably more important than getting the details of the auction format just so. So, this conclusion depends a little bit on the application, but certainly when you have a scarce situation like a single item auction, I think this is pretty good advice. Of course, there's always the case where you are unable to scrounge up more competition, and then of course the optimal auction becomes very important again. But this is still a good thing to know. Okay? So let me tie this. So it's a statement of the theorem. Clear? We'll prove it in a sec. It's not that hard. So just to tie this back in with the critique, right? So remember we were saying what about thin markets where you don't have good statistics about the bidder valuations, or maybe you sort of have something that's volatile, the valuations are changing rapidly over time. What if you're not comfortable tailoring your auction to a distributional assumption? What can you do? Are there good prior independent auctions? So the left-hand side. Does the left-hand side depend on any distributions? Just a second price auction with no reserve, right? It's well defined no matter what. Okay, its revenue will vary as you vary the distribution, but the specification of the auction does not reference a distribution. How about the right-hand side? Does that depend on the assumed distribution F? It does, because it uses a reserve price. The reserve price is this inverse virtual value of 0, and the virtual value is a function of the distribution F. Okay? So if you think about it, really there's an infinite number of instantiations of this theorem as you vary the distribution F. The left-hand side is always the same auction, okay, our protagonist. And as we vary F, it's competing with different auctions, right? Every time we change F, there's a different optimal auction that it has to compete with. And somehow this is saying that the Vickrey auction is simultaneously competitive with all of these optimal auctions across all F simultaneously. Again, under the assumption that you award it one extra bidder, okay? So this is a prior independent auction. It's as good in this particular sense as if we knew the distributions up front. So that's the flavor of research in prior independent auction design. All right, so let's do the proof. So just as in the proof of the Prophet Inequality, where we had two things we wanted to compare, it was hard to compare them directly, and we defined intermediaries that were easier to compare. We'll do the same thing here, except instead of the intermediaries being mathematical expressions, it will be a third auction. Not one of the ones we care about per se, but one that's useful for bridging the gap between the two. So just for the purposes of the analysis, define an auction A with n plus 1 bidders as follows. So first, again, this is all just a thought experiment. So we fixed n, we fixed the distribution F. There's some optimal auction, okay, with respect to F. So in the proof, we envision now with n plus 1 bidders, on the first n bidders, we're just going to simulate opt on them, okay? Which really just means we run a Vickrey auction with a suitable reserve with just the first n bidders. We've left bidder n plus 1 aside in this fictitious auction A, okay? Now you run a revenue maximizing single item auction, you might sell the good, you might not. So if we don't, in this auction A, then as a backup, we give it to the last bidder for free. Okay? It's not clear why I'm doing this yet. I just want to make sure you understand the definition. So auction A simulates opt on bidders 1 up to n. Meaning it picks the highest virtual value bidder amongst the first n if there is one that's positive. If none of them are positive, there's no sale. Give item to bidder n plus 1 for free. Why did I define auction A? Well, it has two properties that allow me to bridge the gap between the two sides of the theorem. So first note that just by definition, this auction's revenue with its n plus 1 bidders is exactly the same as the expected revenue of the optimal auction for n bidders, because it literally just simulated it on a subset of the n bidders. Okay? So by definition, I've equalized revenues. So A's expected revenue with n plus 1 bidders, same as opt, where opt is with n bidders. Okay? Also, something I obviously enforced is that A always allocates the item. No argument there, I trust. So we're almost done. This judicious choice of an intermediary auction makes comparing the optimal and Vickrey auctions a very slick affair. So here's the last thing that we're going to prove, which is also sufficient to finish the proof. I claim that if you look at all the auctions in the world that are guaranteed to sell the item, some auctions will always do that, and some auctions won't always sell the item. But if you just focus on the subset of auctions that always sell the item, amongst those, the Vickrey auction maximizes the expected revenue. So I'll explain why this is true. But first, let's just observe that if we can prove this claim, then we're done with the proof of the Bulow-Klemperer theorem. Why? Well, think about this auction A, right? So, well, first of all, we have opt with n bidders. So it's just some number, 1,000, whatever. I defined a second auction A on n plus 1 bidders that by definition has exactly the same expected revenue, 1,000. Moreover, it always allocates the good. Then by this claim, the Vickrey auction, which of course always allocates the good, the claim says that it's even better. Okay? So the claim says Vickrey has to be better than A, which is equal to opt with one fewer bidder. So all I need to do is prove this claim. So reason, so proof of this, and notice I haven't used my IID regularity assumptions yet, so that better come in now. So suppose I gave you the very weird problem that I wanted you to always sell the good, and then subject to that constraint, I wanted you to maximize revenue. Right? So how is this different than the problem we've already been studying? Well, so now the sum of the xi's has to be equal to 1, not at most 1. Okay? So these bidders show up, they have their virtual values. Right? Some might be negative, maybe all of them are negative. And you've got to give the item to somebody, even if all of them are negative. So you pick the lesser of all the evils. Right? You just pick the biggest virtual valuation, even if it happens to be negative. Because you got to sell the good. There's nothing else you can do. Okay? So if you want to max revenue, subject to always selling good, allocate to the bidder with the largest VI of VI, even if this happens to be negative. Okay? So that's just from the very first thing we said at the beginning of the lecture. Okay? That when you want to maximize virtual surplus, whatever your problem. Okay, so in particular in this problem, you want to maximize virtual surplus. It's regular, so we can do it point-wise. So this is what it says to do. Is there a question over there? Good. So this is the revenue maximizing auction subject to always allocating. And I claim that because it's IID and regular, actually the Vickrey auction is doing exactly this. Okay? So why? So what is Vickrey doing? Well, it gives item to the person with the highest valuation. Generally speaking, not the same thing. Okay? But what are our assumptions? So first of all, it's IID, so all the phi-i's are the same. Okay? Everybody has the same function phi. Okay? What does regularity say? Regularity says it's an increasing function phi. Okay? So if I order everybody's valuations, and I apply this same increasing operator to all of their valuations, I get a different set of n numbers, but they're in exactly the same sorted order as before. Okay? So the bidder with the highest valuation is also the same as the bidder with the highest virtual valuation. So in some ways it's not what the Vickrey auction is designed to do, but it's inadvertently maximizing revenue subject to the constraint of always selling the item. Okay? So that proves this claim, which means the Vickrey auction does at least as well as the auction A, which is equal to the revenue of opt with one less bidder. Have a good weekend. I'll see you Monday.